Hey there, welcome back to 2241. This is the example problems video for section 1.3. We're going to talk about the dot product. All right, so we'll start off with this problem number one. This is just computing things, but it helps us get used to how the dot product works in practice. All right, so we're starting off with some two-dimensional vectors here, 2, 4, and 3, minus 1. And we're just going to use our dot product formula, the algebraic one, that says we multiply x components and then y components and then add the results. So 2 times 3 plus 4 times minus 1. This gives us 6 minus 4 is 2. And there is our dot product. All right, for this next one, we have some three-dimensional vectors, so we have an extra term there, but nothing changes about the formula. We just multiply corresponding components and then add the results up. So we have -6, 7 times 2 is 14, and then 4 times -1/2 is 2, -2. And now we add all of these up, and we have 6, I believe, +6. One mistake that I've seen students make here is to compute the products of these components with each other and then organize the results into a vector here. So they might write something like -6, 14, -2, and then they get stuck because they think that the result of the dot product is a vector when it's not. You need to be very careful about how you write things and make sure that you know when there's a dot between these two vectors, you have to add up the results of these multiplications. And then that gives you the dot product. Because if you get here, you'll be super confused and you'll be like, why can't I solve the problem? Well, it's because you didn't write down the right thing. So don't do that. Just a warning there. All right, next up, we have another three-dimensional vector dot product. But now things are written in IJK form. And I actually want to do this one a little bit differently. So we have IJK here, and I want to propose that we can sort of treat this like polynomial multiplication. So x plus 2y minus z, and then we just multiply these guys like normal, 2y minus z, except we have to have some rules here between x and y. And those rules come from figuring out, all right, what is the dot product of I with itself and with j and k. So I, dot product I, this is 1, 0, 0, 1, 0, 0, multiply, 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 add, add, add. This is 1. For I and j, everything ends up being 0, so we get a dot product of 0. For I and k, same thing happens. It's just a 1 in a different coordinate. And so I dot I gives us 1, I dot j gives us 0, I dot k gives us 0. And so if we write this as in terms of polynomial variables here, this is telling us that x squared equals 1, x times y equals 0, and x times z equals 0. Similarly, we will have that y squared equals 1, z squared equals 1, and then we got yx equals 0, yz equals 0, zy equals 0, and zx equals 0. So this whole matrix of zeros and ones, and that z squared should have been a 1. All right, so we can go ahead and multiply this like a polynomial. We just have to remember that at the end, If we see x squared, y squared or z squared, those are ones. And any combination of these variables that is not just the square of one of them gives us a 0. So note this analogy only goes so far, but I think it is nice to see connections between different areas of mathematics like this. All right, so let's go ahead and just FOIL this out then. So we have x times 2y. You're looking here. So that's going to give us 2xy plus 2y times 2y. That's going to give us 4y squared. Okay, and then plus, now we've got minus z times 2y minus 2yz. Okay, and then we've got all of the products with the minus z term over there. So we have x times minus z gives us minus xz. And then 2y times minus z gives us minus 2yz again. Last, minus z times minus z gives us positive z squared. And now if we look back at our table over here, we see, all right, any of those mixed variables are 0. Anything that's squared is 1. So we can cross out a bunch of stuff here. All right, xy is mixed, 2yz is mixed, xz is mixed, and so is that one, yz. And so what we are left with is 4 times 1 plus 1. And so we get 4 plus 1 is 5 for our dot product there. So probably a little unnecessary, but for other cases, it might be helpful to look at things like this. And again, if you go on to do more mathematics, ideas like that will be helpful. Okay, so here we have in problem 2, u and v are given with lengths, not coordinates, and we're told that they're at an angle of pi over 3 with each other. So there are lots and lots of different vectors that these could be, but this is all that we want. We want their dot product when the two vectors look like this in relation to each other. And, well, we've got a formula for this, and it is the geometric formula. That one only involves the lengths and the cosine of the angle between them. So what we're going to write here is 4 times 6 times the cosine of pi over 3. And cosine of pi over 3, if you don't remember, that is 1/2. Okay, so we've got 4 times 6 times 1/2. Half of 6 is 3, and then 4 times 3 is 12. So there's our dot product of u and v. Note also that these numbers are pretty arbitrary. They could be 5, they could be 6, 2, 12, they could be negative, they could end up being pi. There's no restriction on what real numbers the dot product can be. All right, so next up we have 3. Find the angle between u and v given these coordinates. Right, so in this case, we are going to use the same formula, but we are going to use the version that's solved for the cosine. Because now we're given the coordinates, and we can use those to get the angle. Okay, but now we need the norms of these vectors. Okay, so let's do that off to the side, actually. Save ourselves some trouble here. So norm of u equals square root of 2 squared plus 2 squared plus 1. That's 3. Square root of 25 plus 9 plus 4. That is 38. So the square root of 38 is just the square root of 38. So we're just going to have to leave it like that. All right, so now we take the dot product on top and we have these two things on bottom. Dot product gives us 2 times 5 is 10, plus 2 times minus 3 is negative 6, and then negative 1 times 2 is negative 2. Divide by 3 root 38, and we get 2 over 3 root 38. And what do we get out for that? Check my notes. We get angle of about 84 degrees. So you would take the inverse cosine of this number to get that 84 degrees. But usually it's enough to just find the direction cosine. Okay. So next up, we are going to do number 4. It says, show that these two vectors are orthogonal, so perpendicular. And if we remember our test, we know that u is orthogonal to v if and only if u dot v equals 0. So all we have to do here is multiply these two vectors using the dot product. And I'm going to use our polynomial version again, just because I think it's fun and it makes this a little easier for me. Minus 4j plus 2k. All right, so multiplying this out, we get 10x squared. I know all the cross terms will be 0, so I really only care about the 2 and 4y minus 8y squared plus negative 2z squared. And then I know the squared terms will go away, and I just get 10 minus 8 minus 2 is 0. Okay, so yes, these two vectors are orthogonal, and that's it. Checking orthogonality is very straightforward. Make sure that you know how to do that one. Right here, now we're going to find the direction angles of a vector in the standard basis. So if you remember our formula for finding the direction angles, it is take the, or we're going to find the direction cosines actually, and then the angles will come from that. It was that the cosine of alpha, beta, and gamma is given by the vector u divided by its norm, which is really just the components of the unit vector in that direction. So all we really need to do is find the unit vector, and its components we can take the inverse cosine of to get the angles. So let's see, what's our vector norm here? Because we need that. Square root of 1 plus 4 plus 9. That is, what was that, 14? Yes. Okay, so our norm is 14, and we're going to divide all of these components up here by 14 to get cosine of alpha equals 1 over root 14. Cosine of beta equals 2 over root 14. And cosine of gamma equals 3 over root 14. All right. And then so if you go ahead and take the inverse cosines of these, you should get that alpha is about 74 degrees. Beta is about 58 degrees. These are abouts, not exacts. And gamma is about 37 degrees. Trying to read those from my notes here. Yeah, that's about correct. Okay, so nothing special there. We just find the unit vector, and then its components give us the direction cosine. Take the inverse cosine of those numbers and you get the direction angles. All right, next up we have find the scalar and vector projections of this vector v onto this vector u. So again, we just have some formulas here and we'll write them out. So the scalar projection of v onto u given by the dot product of the two, divide by the norm of the one you're projecting onto. So here we've got, let's see, 1, 1, 2, minus 2, oh, actually I had that a little backwards, sorry. Minus 2, 3, 1, 1, 1, 2. Having them like that. And then divide by the square root of 4 plus 9 plus 1. Again, that's 14. So we got minus 2 plus 3 plus 2. 2's cancel out, and we get 3 over the square root of 14. All right. So notice that that is a number. When we do the scalar projection of a vector onto another, we are supposed to get out a number at the end. And so we did, and that means we're good here. Move this and give us a little more space for the vector projection next. So for the vector projection of v onto u, we had a slightly more complicated formula. But it can also be thought of as use the component, then multiply it into the unit vector for u. So we already know that the unit or the norm of u is square root of 14, and the vector u itself is given. So we can compute the unit vector pretty quickly. And we get u hat equals minus 2, 3, 1. So minus 2 over root 14, 3 over root 14, and 1 over root 14. There's our unit vector, and we just want to multiply by the scalar projection right here onto that. So what we want is 3 over the square root of 14 times minus 2 over the square root of 14, 3 over square root 14, 1 over square root 14. Okay, so the 14, so this is where we need to be a little bit more careful about multiplying. So this is not multiplying like the dot product in that that rule over here. It's not working like rule number 4 here. So we want to make sure that we are multiplying this scalar into every coordinate, because this is now scalar multiplication, not some weird dot product algebra rule that we are just getting used to. So the 14, the root 14 is going to end up multiplying onto all of these, and we should get 14 on the bottom of every fraction here. So what that means, we really only need to multiply the tops to get the answer out here. And that gives us minus 6 over 14, 9 over 14, and 3 over 14. And that is now our vector projection of v onto u. So notice, again, this is a vector now, not a scalar. We should get a vector out of the vector projection. All right, and now our last problem here, this is the one on work. So we have a wagon that is being pulled in the rightward direction, and it's being pulled for a distance of 100 meters. The force that's pulling it is acting in this direction at 35 degrees to the horizontal. And so if we know the size of that force, 70 newtons, we can use our work formula, which says, all right, take the norm of the force, and actually, let's back up a little bit. So the work formula says that work is force dot displacement. But the geometric version of the dot product says, well, we only need the magnitude of the force and the magnitude of the displacement. So once we have those two norms and we know the angle 35 degrees between them, well, we can just go ahead and plug that right in, can't we? So we get 70 for the size of the force, 70 newtons. And in physical problems, I do like to try and keep the units, times 100 meters, and then times the cosine of 35. I don't know exactly what that is, but my notes here say that it comes out to be about 5,000 something, 5734. And then newtons times meters gives you joules, which is a unit of energy. And that's why work is equated with energy. But pretty straightforward. We just had to know, okay, force, displacement, angle, and I want the work. That's a dot product. Once you have all that, plug things directly into your formulas, and you're good.